algorithm, which is the one of the most popular, widely deployed in several commercial applications and engineering problems. The algorithm is widely deployed algorithm and has, in fact, the overall AI research, artificial intelligence research. If you've studied the history of the artificial intelligence, 1950s, when the artificial intelligence research started, the scientists were promoting the symbolic AI. Okay, so the rule-based systems, symbolic-based artificial intelligence, that was dominating the AI research. Of course, the neural networks and connectionistic approaches, brain-inspired models, that research was also going on. But only when the backpropagation neural networks were introduced and when they were proved to be successful models, only then the popularity of the connectionistic models has increased, and researchers and scientists were started seriously working on the neural network models. So in that way, backpropagation neural network is one of the most significant neural network one should learn, and also it is like a foundation for the deep learning models that you may be studying in the future. Okay, so as we discussed, today we will actually work out with one particular problem. As we have seen in the previous class, you can notice that okay, so we are giving the inputs. We have a hidden layer of neurons, and of course the diagram what we have drawn here is only a single hidden layer, but we can have more than one hidden layer also, and the hidden layer is having two nodes. You can have more than more nodes as well. Okay, so now the activation propagates in the forward direction. Then you calculate the actual output at the output layer. Once that is done, we are checking what is the error, right? Once the error is calculated, remember the way that we are going to calculate the error is target minus actual into the first derivative of the activation function over the particular net input. So the first derivative of the activation function gives you the rate of change of the error with regard to the corresponding weights. Okay, so that is the reason why you are going to calculate the first derivative of the activation function. And in fact, this first derivative or the derivative of the activation function is called as gradient. Okay, the gradient. So the algorithm, backpropagation algorithm, is generally regarded as gradient descent model. Okay, gradient descent model. We will be discussing this little later. So gradient descent model, the reason is that the first derivative of your activation function with which you are going to measure the rate of change of the error with regard to the corresponding connection weights, and that is getting propagated back to the previous nodes. That means, from the output layer to the hidden layer by multiplying the gradient with the corresponding connection weights, and hence again in the hidden layer we are calculating the hidden layer connection weights, hidden layer gradients. Okay, and that gets propagated to the input layer. Okay, so in fact, I have already given, if your activation function is a unipolar sigmoidal activation function, that means 1 by 1 plus e power minus net, the way you have to calculate, that also we discussed, right? So these things we have discussed. Then also we discussed about the way the weights are to be modified. Okay, how the weights are to be modified. The weights to be modified at the output layer. Similarly, the weights to be modified between input layer to the hidden layer. Okay, So these things we have discussed in the previous class, and this is the algorithm. Okay, so this is the backpropagation algorithm. Whatever the steps we have narrated are found, you can find them here in the form of a formal algorithm. So you can notice that initially we are going to initialize all the connection weights to some small random values. Okay, then till a stopping condition is met. Typically the stopping condition is your t minus o is 0. That is what is the stopping condition. But in some of the applications, this t minus o may not become 0, but it reaches to a very epsilon, which is almost close to 0, but it's not close to 0. So you have to see, and then accordingly you fix the stopping condition. Till you stop, you have to train the model. So you need to pick the training feature vectors and then proceed in the feed forward direction, right? So that's what is discussed here. Then when you proceed, you calculate the activation, set input to hidden, and then subsequently get the output from hidden, submit it to output layer, and proceed like this. Once that is done, okay, you have finally calculated the output at the output layer. What we are doing it is at the step 6 is calculating error at the output layer. Okay, when you are calculating the error at the output layer, as we have seen, t minus o is there, and in addition to that, your first derivative of the activation function is also given. In fact, I have given you the formula of first derivative of the activation function. So once that is done, you are going to propagate that error back to the previous nodes, and you are going to adjust the weights between output and hidden nodes. Similarly, you are going to calculate delta for each hidden nodes, right? And propagate it. You are going to calculate the error terms for the each hidden layer, then compute the new weights for the hidden layer to input layer connection weights that are to be adjusted. So how we are going to adjust the connection weights, that formula also we have discussed the other day. Okay, is that clear? The algorithmic steps. Any doubts?
Clear, sir.
Okay, now let us take one small problem and then try to work out and see that how actually it is getting done. So let us take a small problem where you have two input connections that are connected to two hidden nodes, okay, Z1 and Z2. All of you please take pen and paper. Also, I suggest if you have a calculator, scientific calculator, please keep a scientific calculator with you. And also it is better that when you are going for the examination, you need to keep this calculator with you. Okay. So the two bias we are having to both Z1 and Z2, and the values please note down. The input at X1 is 0, input at X2 is 1. Okay, this is your feature vector. So 0, 1 is the feature vector. And the connection between X1 to Z1 is the connection value is 0.6. And the connection value from X1 to Z2 is minus 0.3. Then X2 to Z1 connection weight is minus 0.1, and X2 to Z2 is given as 0.4, 0.4. So this is 0.1, minus 0.1, this is minus 0.3, this is 0.6, and bias to Z1 connection weight is 0.3, and bias to Z2 connection weight is given as 0.5. Okay, now you have an output node Y, and so Z1 to Y is 0.4 and Z2 to Y is 0.1. You have the bias connection to Y with a connection weight of minus 0.2. Okay, so This is the initial this one, and the initial your learning parameter value is 0.25, and you are asked to do this problem for unipolar sigmoidal. So 1 by 1 plus e power minus net. That's what is the this one. And then for 0, 1, the target value t is 1. Okay. Okay. Is the problem clear?
Yes, sir.
So let us do, remember, while we are doing this, typically we do this for for one iteration when we are solving it in the class, and also when you are solving it in the examination, typically you do it for the one iteration. But obviously you have to, when you are writing a program, you need to see the stopping condition. Right. So now let us do so please, first, what is that we need to do? First, what we need to calculate? Net Z1, right?
Net Z1, net Z2.
Yeah. Please tell me what is net Z1 and then net Z2. So you have Z1 is receiving input from X1 as 0, X2 as 1. Of course, you have bias, which is 1. Okay. Yeah. So what is net Z1? So essentially X1 is 0. So 0.
0.4.
Can you please check it here? See, this is X2. X1 is 0. X2 is 1 into minus 0.1. Remember, the connection between X2 to Z1 is minus 0.1.
Okay. Sir, then it would be 0.2.
Okay. All of you have got it. So what about OZ1? It is 0.5498. 1 by 1 plus e power minus net Z1. Similarly, what is net Z2?
0.9.
OZ2? So this would be around 0.7109. Is it not? Now tell me what is net Y. So output from Z1 is OZ1 into the corresponding connection weight, and output from Z2 OZ2 and its corresponding connection weight goes as, of course, you have bias and corresponding weight goes as an input to Y. So what is net Y?
Here is it 0.72.
What is that? Which one you are saying? Net Y.
Why?
Net Y. Okay.
0.726.
Net input to output layer is no, here it is coming somewhere around 0.09101, something like that. Please check it. So So what we are doing is OZ1 into the corresponding connection weight 0.4, then OZ2 and corresponding connection weight 0.1, bias is 1 and corresponding connection weight minus 0.2. Please see the the symbols. It is plus and minus symbols carefully, and tell me what is the actual output. It's coming around. It's around somewhere around my 0.5227. Okay, up to now, is that clear?
So we are calculating OZ1 by using, sir, 1 upon 1 plus e to the power minus lambda, right?
Yeah, yeah. So I have written the your activation function, target
Yes.
function,
Okay, sir.
1 by 1 plus e power minus lambda net.
Okay, sir.
So yeah, so your actual output is 0.5227 and the target is 1, right? So so we need to calculate the fourth step. Error term at output layer. So here output layer you have only one node, so at y, right? So error term at y, that is del y. So how do you do that? So the error term del y is equal to what is the formula? So target y minus actual y into f
Derivative of
dash
net.
derivative of your net net y, right? So this comes with the formula your f dash net y for 1 by 1 plus e power minus net. What is that we have set? With
So
that you
lambda into
so
f net y.
yeah, now anyway, since lambda value I have given 1, or lambda value is not given, so you remove lambda. So what you get is, yeah, so ty minus oy into
Into
what
f
is,
net y into 1 minus f
okay,
net.
f net, okay, f net y is your ozy, right?
Yes, sir.
So okay, it's not ozy, it is oy. I'm sorry, this is oy. Okay, this is oy into um, 1 minus oy, right? So ty minus oy into oy into 1 minus oy. Okay. So tell me what is del y. Remember, if you have one more node in the output layer, you have to calculate, say take an example, you have y2, then you have to calculate in the similar manner del for del y2 as well. Okay. Yeah, so can you tell me, so target is 1, actual is 0.5227. So 1 minus 0.5227 into 0.5227 into 1 minus 0.5227. Okay. So what is the value you get?
0.119.
So somewhere around you get, so 0.1191. So now the point is we have got the error at the output layer. Now let us calculate, not calculate, let us propagate. Okay, propagate error to hidden nodes Z1 and Z2. calculate del z1 and del z2. Okay, so what is del z1? So del z1 is error at the z1. So what is the way to calculate the error at z1?
Sir, del y into the
So del y into what is the connection weight? We
weight of
have to
z1.
consider w z1 y, right? When you are considering del z1, I'm going to consider the connection weight between z1 and y. Correct? Okay. Yeah, tell me.
Into derivative of f net
F
z1.
dash
F dash net Z1.
f dash net z. That's all. So obviously f dash net z1 is, the f net z1 minus 1 minus f net z1, and you have del y, you have del z1 y. Sorry, you have wz1y, that means the connection weight. So with that, what is the error term at del z1?
Sir, is it 0.011?
Okay. Are everyone, are all of you are able to follow, or only one or two students? You have any doubts? Hello, yeah. Everyone, all of you are
No
able to
doubt,
follow.
sir.
Okay.
No doubt, sir.
Now imagine you have two nodes in the output layer, y1 and y2. Then what would have been? Sorry.
Sir, what is the answer? Like, okay,
Yeah,
0118.
JD. Imagine, yeah, 0118. Imagine you are having two nodes in the output layer. Then what you are going to do for this particular term? I'm just writing in case if you have two nodes. I'm writing here. So you have to make it as del y1 into wz1 y1, and you are going to plus del y2 if you have a y2. Of course, for this problem you don't have y2. Del y2 and weight from z1 to y2. Like that, you have to add how many number of output nodes you have, that many corresponding dels would have got propagated back to z1. Hope you got it, right?
Yes, sir.
I'm just writing here, don't get confused in case tomorrow if again you see if y1 y2 are there. Okay. Similarly, now let us try for error term at z2. So obviously you have one node from the next layer, that is del y, and you are going to consider weight of z2 y with derivative. Of course, I am telling gradient. Okay, the gradient at z2. So f dash net z2. Okay. Okay. So now tell me, what is the value for del z2? The error term at
So
z2.
0.002.
0.00024.
4.
Okay.
Sir,
So yes, please.
sir, in the del Z2,
Hmm.
del Y will be 0.1191. WZ2Y will be like 0.1, right?
Exactly. See, I have
And
written here. Yeah, WZ2Y is this one, connection between Z2 and Y.
okay, actually, I'm getting a different answer. That's why I'm asking. And F dash net Z2 will be 1 minus 0.7109, right?
Yeah, it is like this. How do you calculate f dash net Z2? It is f net z2 into 1 minus f net z2.
Okay.
See the first derivative how you are calculating, like how we have written here. You see first derivative.
Yeah. Okay. Noted.
Okay, so don't get confused and remember this f dash net is for the activation function 1 by 1 plus e power minus lambda net. If your activation function is 1 minus e power minus net by 1 plus e power minus net, then the derivative gets changed, right? So depending upon your activation function, your derivative accordingly gets changed because you are derivating the activation function with regard to the weights. So that's the reason why dou by dou w you are making it. Okay, so accordingly you have to write the error calculation thing. So typically, see, with regard to your examination point of view, we are going to either use unipolar sigmoidal or bipolar sigmoidal. So in that regard, you just remember the f dash corresponding f dash. Any doubts? The other students, are you able to follow? So once this delts are done, that means you have now calculated the gradients for Z1 and Z2. Now the point is that weights are to be adjusted, right? So let us go to the next steps. That means the uh, so weight adjustments. So now at output layer. Okay. Output layer you have the weights for W Z1Y, then you have W Z2Y, then you have WBY. Is it not? So now tell me what is the way out for this? How to adjust the weights? We have already mentioned in
The
the
old weight plus
yeah. All of you note this. Old weights plus your, if it is at the output layer, old weights plus the learning constant, the corresponding error term at the layer. Of course, now we are going to call it as a del y, and f net y. That means the actual output, right? So you note down what is the actual output at y is my 0.5227, right? So tell me. So volt plus alpha del y into rho y. Please tell me the
So can you show the weights once more?
yeah.
The old weight.
Please note down this. So error term is what is del y is 0.119, and yeah.
Sir, 0.4622.
1 minute,
First
1
one.
minute. Yeah. 1 minute. We will come to that. Let me 0 point.
Mine is
462.
0.4155.
The new weight from Z1 and Y, right?
Yes, sir.
What is the weight? Weight from Z1 and Y?
0.4.
0.4155.
Actually, 1 minute. This is okay. This particular term, there is a minor clarification needed here. Old weight plus learning constant into the error, that means del y, and this is the corresponding connection input. So it's not exactly OY, it is the input that is coming from Z1Y. That means it is OZ1. Okay, you need to, if when you are calculating it is Z1Y, it is OZ1Y. Okay, are you able to follow what I'm talking? This is learning constant. This is error term. This is input at on that connection. Okay, so now we are calculating the connection weight, new connection weight between Z1 and Y. So when you are calculating the new weight between the connection weight between Z1 and Y, whatever the corresponding input that is coming in from this particular connection, what is the corresponding that is coming in is that OZ1. So that's what we need to look at it. Okay, is that clear? So that means
Yes, sir.
output from Z1. Okay, that is 0.5498. So I hope that that you have to. Though I write here output, this is the output from the previous layer coming as an input over the connection. That please get clarified. Okay, this is not OY. This is the output from the previous layer coming as input to that particular node. Any doubts? Shall I repeat?
Sir, it will be O of Z1 or O like Z1 via the connection weight. It will be O of Z1, right?
Yes, yes. So we are modifying the connection weight Z1Y. So corresponding input coming from that output. So that is OZ1. Okay. Now tell me, I think this this number is wrong.
Sir, 0.4163.
Yes, sir, 4163.
Yeah. So please, all of you remember once again, when we are modifying the connection weight, we are going to look at the corresponding input over that particular connection. In this case, it is an output layer. So that is the output coming from the hidden layer. Okay. And hence, now take an example, we are talking about Z2Y. So the old weight plus the learning parameter, learning constant, then error term, that means the del y. But what we are going to adjust here is that the corresponding connection input. The corresponding connection input is the output coming from that hidden node, that is OZ2.
So it is the answer 0.121.
Yes, it is 0.1211. Okay. And it is bias. So W X1 Z2 X1 Z2 X2 Z2 X2 Z2 PZ1. Okay. So what is bias to Y?
minus 1.7.
Yeah, somewhere around minus 1.71 kind of thing, or 1.70. Okay, so this is how your weights at the output layer are getting adjusted. Now then we need to adjust the connection weights between input to hidden. Again, so the old weight plus we are going to modify the connection weight between input to hidden, that is Z1. So corresponding del Z1 and the input that is coming over the connection X1 Z1. So it is X1. Okay. So now tell me what is the adjustment that comes there. So what is the input pattern we have given? It is 0, 1, right? X1 Z1. Sorry, X1 X2. So the new weight for what is new weight for X1 Z1?
Sir, won't it remain same?
Yeah, so you are having, since it is X1 is 0, X1 coming, X1 connection input coming is 0, so it remains 0.6 volt weight. Yes, correct. And what about X1 to Z2? Obviously, it would all be the same 0.3 because your input connection is 0. Okay. Now X2 Z1 please. So what you do X2 Z1, you have to see the volt weight, then the learning constant, the error term is del Z1, and the input connection coming over the connection X2 Z1, which is 1.
Sir,
Sir, minus
0.10.
0.0705.
Sorry, can you please repeat? Minus
0.0705.
0.0705.
Yes, sir.
Minus 0.078.
I think it is 0.9705, something like that. It is X2 Z1. And similarly X2 Z2, that would be around 0.4006.
Oh, sir,
Yes, please.
in X2 Z1, it will be like W old plus alpha into del Y into order of Z1, right? Or like
The input that is coming over that particular corresponding connection, right? So your okay, what is the volt weight?
minus 0.1.
Okay, plus learning constant 0.25.
0.25 into 0.119. The del Y will be 0.119, no?
Del Z1, right?
Yes, sir.
Del Z1 is 0.
Okay, del Z1. Del Z1 is 0.021.
Del Z1. See, we are talking about which connection weight? X2 Z1, right?
Yes, sir.
If it is X2 Z1, your volt weight plus alpha, then the Z1 what we are going to see is the del Z1. What is del Z1?
0.021.
No, it is 0. Okay, what is del Z1? See, del Z1 is 0.0118, right?
Okay.
And the connection input, so that is 1. Okay. So bias to Z1, it is around 0.3, 0.302, and bias to Z2 is 0.5006, something like that. Okay. So now, okay, this is how you get the new connection weights. Okay. So once you get the new connection weights, the typical process is that again you present the input. Okay. So imagine you are having another feature vector, say 10, 11. So you present the next feature vector and go for the activation propagation. Then check the actions and corresponding for the corresponding input. What is the desired output? That is the target. Then we calculate the gradient. So the point is, each time whenever uh, whenever we are trying to learn, whenever we are saying we are going for the next iteration, what is our objective? What is our objective? So the objective is that your target minus actual should become 0, right? That's what is our objective, right? Hello?
Yes, sir.
So that is the objective. Our why? What is the purpose of learning? You have to see that your target and actual both are same. Now, the point is, in this process, what we are trying to do is this particular error term, our gradient, we are trying to minimize it. Okay. For this type of problems, what we are doing is we are trying to minimize it. There may be some set of problems which we may be thinking or trying to do to maximize the objective function. Those are all called gradient maximization problems. What we are solving here is the minimization problems. So the objective function, what we are considering, first of all, should have the property to become to be able to calculate the first order derivative for that. Okay. So that means you should be able to calculate the gradient. Number one. Number two, once we calculate the gradient, we keep trying to minimize the gradient and reach to a point where that minimum point is not the local minimum, but it is the global minimum. Okay, so you guys need to remember this also. The minimum point what we are trying to find out should not be the local minimum. So that means, imagine if you try to plot your gradient descent, that means your minimization of the objective function is when you plot. Okay, when you plot, imagine it goes like this. Okay, now if you notice in the graph, actually you have to come to this point. But now if you notice, when you are slowly moving downwards, you may come to this particular point. This is the local minimum, called a local minimum. One should not settle down at this local minimum, but should still propagate, should proceed further and try to find the global minimum. But majority of the cases, majority of this gradient descent algorithms like backpropagation, they have the tendency to settle down in the local minimum. Okay, so for that there is a separate boosting is required, optimization is required. That is altogether different concept of learning, which I think when you are moving towards machine learning algorithms, learning machine learning algorithms, optimization, those places we will be learning it. So that is one thing. Second thing is okay, now so this is also called as the backpropagation algorithm is also regarded, or else it is regarded as a category of gradient descent algorithms. So if you notice any of the gradient descent algorithms functionality, it is the typical like backpropagation kind of a thing, or else you can say that backpropagation is actually following the gradient descent model of learning, where what you do, you present the input 0, 1, and for that purpose initially you have taken some random initial weight values, some initial values, then you present the input, then calculate the activation. Once you calculated the activation, then you go for calculation of the gradient. Right. So when you calculate the gradient, what you are doing is you are trying to know what is the error part. Now for that you are trying to minimize it. What is the steps that you are doing to minimize that? You are going to adjust the connection weights. Once you do that, again you present the input and proceed further. Okay. So you are presenting the input and you are trying to search over your gradient space to find that minimum point where your that particular error it is reaching to the that least point. Okay, global minimum point. So this is how we have to proceed. As I've already said, for your examination point of view, you need to focus on this type of problem. So let us try, all of you please note down this particular problem and try to work out it back at home. Okay. So one more problem I'm giving just for your practice purpose. So you have Z1, Z2, and input is coming from X1, X2, right? So you have the bias here, and now for your understanding purpose, I am giving you the two nodes in the output layer. So Y1, Y2, okay, both are having bias. Now connection weights from Z1 to Y1, Z2 to Z1 to Y2. Similarly, Z2 to Y1, and so this is bias and this is also bias, and this is 0.5, this is 0.7, and x1 to, okay, so x1 to z2 it is minus 0.6, this is x2 to z1 it is minus 0.1, and bias to z2 is 0.4, bias to this is 0.2, and bias to y1 is minus 0.4, this is 0.6, and z1 to y1 is 0.3, and this is 0.8, and this is z2 to y1 is is 0.2, and this is 0.5. Okay, so please try for unipolar sigmoidal, 1 by 1 plus e power minus net, and also the same problem for bipolar sigmoidal, 1 minus e power minus net by 1 plus e power minus net. Okay, so try this with the alpha value 0.3. Okay, and give the input x1, x2 as 1 and minus 1. So the output at y1, so that means you are going to have the two targets. So target vector is minus 1 and 1. Sorry, okay, see we said unipolar, right? So you please take it as 0. Okay, then you take it as 0. Okay, 0. Okay. If it is a bipolar, you please make it as 1 minus 1, and then so that means for bipolar you take the bipolar inputs and bipolar targets. So this becomes minus 1 and 1. Hope that is clear. Okay. So please try this so that you get more familiarity. If you are getting any doubts, please come back and see. Okay. With that, we have concluded the first module. So we will be having quiz, a formal quiz for the internal assessment that we will be conducting it in the next week. So from the beginning, whatever till back propagation